Okay, sorry about being late. My machine crashed, so I have to restart my machine. Okay, so can everyone hear me? Would you say yes? If you can hear me. Okay, good. Thank you very much. So we will continue discussing about the resolution proof system for first order logic. And as I told you before, the key difference between what we are covering now and what we studied before is that the the resolution proof step in this case will involve not just canceling the complementary literals, but also instantiating some variables. So beforehand, replacing variable by ground terms, and then canceling complementary literals are done in separate steps, and they didn't really interact with each other. In this first order resolution proof, these two things are happening at the same time. And the reason is for doing this is, we want to do in some sense by need or on demand groundings of variables in the formula that we are given. So we talked about one key concept in this whole process is called unification and the most general unifier. So this is where we stopped the last time. And the idea of let's see my pen. Right. So in this lecture, we will never deal with the formula, quantify the formula. Everything we are dealing with is quantify a free propositional formula. So some of the issues that I talked about regarding the use of substitutions doesn't really appear. For instance, in this case, if we have a formula F and apply substitution, and then apply another substitution W prime and theta prime, that's always the same as F with applying the composed substitution, theta and theta prime. So this is a composition of two substitution. And then this is a application of one substitution after the other substitution, okay? So, sometimes if you are familiar with group actions and so on, this means at least the idea of applying substitution satisfies so-called monoid actions. But anyhow, this is a property that I told you doesn't hold in general, and that's because of a quantifier. But in this simpler context, it's always going to be true. Okay. So anyhow, so here's the definition, reminder of what unifier means, and then also the notion of most general unifier. When we talk about unifier or most general unifier, we are always talking about a set of literals, okay? So we are given a set of literals. Literal is nothing but basic predicates with some term T1 up to Tn, or its negation. Okay? And then these T1 up to Tn do not have to be grounded terms, so they can have variables. So we have a collection of these literals, and they correspond to collection of literals in propositional logic. And then this set means a disjunction of these literals. And then the unifier is a substitution such that if we apply this substitution to every literal in this set becomes a singleton set. Okay. So for instance, if we have a set of literals P of X and P of F of Y, and one unifier is the one that you see on the screen, which replace X by F of X, Y by A. That's because if we replace X by F of A, we will get this guy. And also Y by A, we get the same thing. So the two things become the same. So that's why this substitution is called a unifier. And the idea of a most general unifier is that it's a unifier which make as few assumptions, which is as little specific as possible. Okay, well, which is as general as possible. In the following sense, okay, it doesn't really. So if you think about how we obtained a unifier, we obtain unifier by replacing variable by something more specific. So for instance, here we replace variable x by f over a, which is a more specific term than variable x. So x represents anything, f over a represents only one specific things. We replace y by a, which is something, a is much more specific than variable y. So we make these two letters in this set D to be identical by changing variable to something more specific. Okay. So the idea of most general unifier is, exploiting this specific. It's tried to be as little specific as possible. The definition say it's a unifier. So theta is a most general unifier of a set of letter D. If first it has to be a unifier, so that's a condition 1. But then it's among the unifier is the most general one. So that's what this second condition say. Whenever we have other unifier theta prime, the theta prime should be reconstructible from the theta by composing some other substitution theta double prime. So theta prime should be obtainable from theta by composing another substitution theta double prime. I don't know whether this help you or not, but if I said the substitution can be understood as a mapping from term to term. So you can think of substitution as a mapping from sigma terms. So sigma is a signature and sigma terms. So this is second condition is saying we have a substitution sigma prime. And then so theta, if theta is the most general unifier, whenever we have a substitution theta prime that make everything in D to be the same guy, then there always exists substitution theta double prime, such that if you compose the theta and theta double prime, that's gonna be same as the theta prime. So people use the word, there's a theta, the phrase like theta prime factored through theta. That's because it can actually be obtained by first applying substitution theta and then applying something else. Okay, so that's the definition of most general unifier. And here are some questions I want you to think about. Okay. So the first question is most general unifier is unique, which so in this context, we are fixing. So for a fixed D, so D is a set of letters. So given a set of letters, I'm asking whether most general unifier is unique. And then second question is does it always exist? So if it doesn't exist, I want you to come up with a counterexample which illustrate two most general kind of reasons why the MGU, most general unifier, doesn't exist. And the third is that now assume that the D, the set of letters, is unifiable. So that's a much kind of, we are not just assuming any set of letters, we are assuming unifiable set of letters. So then we are asking the following question: does most general unifier exist in this specific case? So that's a, kind of easier questions, well, more likely to be true than the other question, which is given any D, MGU exists. Okay, so try to answer these three questions. I will give you 5 minutes to do so. Okay, so let me go through this question. The most general unifier is no. The answer is no. The example is, the very simple example is this. If D is, so here I'm assuming if MGU exists, is it going to be unique? There is a very simple example where you have a P of X and P of Y. So then one most general unifier is replacing X by Y. So that's one most general unifier. Another most general unifier is replacing Y by X. So both of them are most general unifiers. Okay. So the answer is no in this case. And then does it always exist? That's again the answer, when it doesn't exist. So it doesn't always exist. And actually the bit better question is, when doesn't a unifier exist? So there are two typical cases where unifier doesn't exist. So the one example is given like this. Suppose I have f of x and p of g of y. So in this case, if you look at this, what kind of literals we have, both of them start with p, so that part is okay. But then it's gonna start with one case. It start with f, function f applied to x, g applied to y. So however we replace x and y, we will never be able to make f of x and g of y to be the same if they start with two different function symbols or two different constants. It's impossible to make them equal by substitution. So that's one typical case. And then, so the other case is like this. This is, maybe less clear. So if you have a case like this, in one case we have a f of x, the other case we have x. Now, if you want to apply substitution, then you might say, okay, what about just replacing x by f of x? So then if you replace x by f of x, then this term will become p of f of x. So it looks like it's going to get closer to the one on the left-hand side, but the left-hand side becomes even longer. It becomes f of x. This pattern will continue. Whatever substitution you think about for x by the sigma terms that we talked about so far, you will never make them equal. If you extend the language, this is not what we are talking about, but if you extend the language by allowing infinite terms, then we can make them equal. But for finite terms, you will never be able to make them equal. So this is another typical example. In the corresponding position, one case you have a one variable, another and term, and then these two variable and terms both have this variable x appears in a term that we try to make them equal. Okay, so that case we won't be able to make them the same by applying the substitution. This is the case where we have two terms which needs to be the same, but they start with different symbols. So it's not a variable and term case, but two different term case. In this situation, we will never make them equal. Okay, so these are the two typical examples of when when a unifier doesn't exist. And right, the last question is, if the set of literal is unifiable, then it turns out the most general unifier always exists in this case. The answer is yes. Okay. So, this is not an entirely obvious question. It's possible that unifier exists, but most general unifier, which say any unifier can be obtained by making some, so if theta is the most general unifier, that means any unifier can be obtained by making theta more specific. Okay, so that's what this definition of most general unifier said. And this may or may not exist. It's not entirely obvious, but it happens that for first-order logic, if set of literal is unifiable, then most general unifier exists. So that's what we're going to talk about next. So this is called the unification theorem for first-order logic. It says that a unifiable set of literals D has a most general unifier. Okay, so if it's set of literal is not unifiable, then we don't say anything about this. But if set of literal has at least one unifier, then it should have a most general unifier. Okay. Now, how to prove this? The proof is actually by an algorithm. So this algorithm given a set of literals, it actually answers whether this set of literal is unifiable or not. If it is unifiable, it will produce a most general unifier. Okay, so that's what the algorithm does. So it's given a set of literal D, and then it either say this set of literal is not unifiable, so it returns fail, or it returns a most general unifier. I will call it MGU. So it will return MGU of D. Now the way algorithm works is like this. So it works by maintaining some internal variable theta and keep updating theta. And this update process will make theta more and more specific. It will, okay, so it will, initially it doesn't do anything, so it's just an identity substitution, but it will make theta more and more specific while the algorithm runs. And if this loop terminates, it will output theta. So that's the case where we have a most general, D is unifiable, theta is a most general unifier. But sometimes this loop can fail, then it will return the failure. Now the body of the loops, so the loop continues until theta is a unifier of D, which means that we apply theta to every literal in D. So if D is L1 up to Ln, so you apply theta to all the literals there. If they becomes one singleton set L, then we are done. So if that's the case, we get out of the loop and return theta. Otherwise, it go into the loops. So that's the case where, so if you go into the loop, that's the case where you can't find, for any L, you can't really make them equal. So there are two, so say Li theta and Lj theta, they are different, okay? So that's only then we go into the loop. For some I and j, they are, after substitution, these literals are different. So then we look at these literals, okay? This which is just, that what you get after applying this current substitution theta. And then we try to find the leftmost position at which these two guys are differ. So if these two literals, if they may start with f, and then maybe after substitution, the first guy is f of x, the second guy is g of y. The Lj, maybe say, the first is f of x, second, maybe just merge. So f of y and then z here. Then maybe z of k of z and w. So it may be of this form. So then it go from the left and then see that we try to find the leftmost position where these two literals are different. So p is the same in both cases. F of x is the same in both cases. G is the same in both cases. And the different places is, in this case, is one is in the variable y, the other case is k of z. Okay. So it first identify the place where two terms are different, and then you check whether this is the case where one is a variable and then the other is a term which doesn't contain the variable. So in the specific example that I'm showing you in the, right now, the one term is variable y, the other term is k of z, which doesn't contain y. So that's the case which may satisfy the condition of this conditional statement. So one of the corresponding subterm is a variable, the other term t, in this case k of z, doesn't contain variable x. In this case, variable x is y, so this k of z doesn't contain y. So if that's the case, we extend the substitution or make substitution more specific by saying our new substitution theta is going to be old substitution where composed with one more step, which is replacing y by k of z here. Okay, so that's how we update the substitution. Now the failure modes happens for many reasons. Okay, we see something different. So this kind of failure mode happens when the two different literals we obtained, maybe they are completely different. Maybe one is talking about P, negation of P, the other is talking about Q. I mean, if that's the case, then they are completely different. So whatever we do with the substitution, we will never be able to make them equal. So then that's the case where we get fail. Another possibility is one case we have a P, maybe just like f of x, and then g of y, the same thing as before. But this case is one of those two cases that I mentioned before where the unification fails. So we have a k, but this time we have a variable y here. Okay, so this is the leftmost terms where these two things are different. One case have a variable y, the other case is a k of y where y appears. So that's another case where the unification detect a failure and then it return, it stop and then say it's not, the given set of literal is not unifiable. Yet another case is the following. Instead of having y here, now suppose in one case we have a k and then, but in another case we have say h of maybe h of a and w. So then these two terms, the different parties h of a and k of y, and they are not variable and term case. They start with the two different function symbols. And again, whatever we do with the substitution, we will never be able to make them equal. So that's another failure case, which is related to the one of the failure case of unification. There is another unifiable terms that I mentioned before. And then if something like this happens, the algorithm also stop and then return the failure. So then it continues. Okay, so that's how this algorithm works. And now here are two exercises I want you to do. The first exercise is to run this algorithm for these two examples. So set D is in one case is P of X and P of F of Y. Another case is, the other case is the D is P of X comma Y and P of F of Z comma X. Okay, in this case, they run the algorithm. Both cases, the algorithm succeed and return the most general unifier. Try to compute the most general unifier according to this by running this algorithm. The second is a more difficult question that we want to actually discuss a bit further and think about why this algorithm is correct. So the correctness often involves two things. One is what this algorithm has to terminate all the time. So first, make sure you have some arguments which say why this algorithm always terminates. And then second, we want to argue this algorithm is correct in the sense that if D is not unifiable, the algorithm returns fail. If D is unifiable, it returns a most general unifier. So the algorithm can serve as a proof of this unification theorem. And then to do this is often done by the so-called loop invariant that we used before when we discussed other algorithms before. So try to come up with a loop invariant, and that's good enough to show the correctness of this algorithm. So I will give you another 5 minutes to do so. Okay, so let me show you the answer here. Okay. So let's first run this algorithm with specific input, which is P of X and then P of F of Y. So D is equal to P of X and P of F of Y. So initially, when you go into this first step, the first step is just set theta to be the identity substitution. So which I will just write it like a blank, which doesn't do anything if you view it as an operator when we apply this substitution. But then if theta is not, I mean, if you don't do anything on D is not a singleton set. So this identity substitution is not a unifier for D. So we go into the loop, okay? And now we try to pick two distinct literals in d theta. So d theta in this case is identical to d, which is p of x and p of f of y. So we pick two different literals after substitution. They are p of x and p of f of y, and try to identify the first leftmost position where the difference appears. And that is, in one case, it's an x and it's f of y. And that's exactly the good case according to this conditional statement. In one term, one literal, we have x variable. The other, we have a term f of y, which doesn't contain this variable x. So that's a good case. So that then the algorithm said extend the theta by adding substitutions, which is to replace x by f of y in this example. So then, so we go to this true branch where we do updates. Then update is like this. So if you go to the loop again, okay, not before going to the loop. So now I have this result is the substitution f of y, the replacing x by f of y. Now, if we apply this new substitution, so let's erase this, maybe this round. When you go into the loop again, now our substitution becomes f of y x. If we apply this substitution d theta, then our set is now the same as p of f of y. Just that's it. I mean, the right-hand side remains the p of f of y. So it's a unifier. It's a unifier. So we get out of the loop and then return theta. So the algorithm said in this specific example, the most general unifier, which is claimed, I mean, the most general unifier, that's what the algorithm claims, is going to be replacing x by f of y. So that's how the algorithm works for first example. For the second, so we have p of xy, I mean, our d is different, p of x comma y, and then p of f of z and x. So, and then our substitution initially is an identity. It's a blank. And then when you apply the substitution, of course, this is not a unifier, so we get into the loops. If we go into the loop, then it identifies the places where the difference appears, which is one case we have x, the other case we have f of z. So that's a good case because one is a variable, the other is a term which doesn't contain that variable. So we go to the true branch, and now after the true branch here, then our substitution is replaced by this guy. So instead of the empty, now we have a substitution, which is x is replaced by f of z. So that's what we have. And then now if you apply the substitution here, so d theta, we're going to have p of f of z, y, p of f of z, and f of z. Okay, so that's what we have. Now this time, if we do the same thing, we detect the place where the difference, leftmost place where difference happens. That's in one is a y, and then f of z. And that's, again, satisfy the condition of this conditional statement, which means that we're going to extend our substitution with one more step, which is now write a different color. So the next step is going to be replacing y by f of z. So that's our new substitution. Now, if you apply this new substitution, and then the set is going to be like this, f of z and f of z. And then right-hand side is again that remain the same. We have a p of f of z and comma f of z. So it's a unified. So we get out of the loops, then final outcome theta is going to be in, okay, I don't have to write. Yeah, the final outcome theta is going to be this one that we have just computed here. So that's the result of running this algorithm for the second example. Okay, I hope that you have a good idea about now how this algorithm works. And this algorithm is correct, actually. The answer for the first is yes. And then we're gonna look at in more detail in the next slides, but it terminates. That's because each iteration of this loop will reduce the number of variables that appears in the set of letters D, okay? So whenever we extend substitution by this extra step, T will not contain variable x. That's the one of the condition of this if then else statement, which means that if we apply substitution theta, variable x will disappear completely. So, and then in order to go into this loop, into this if then, into the true branch of this conditional statement, variable x should have appeared somewhere inside the, so x is chosen, some variable appearing in d theta, okay? So if we keep applying this operator, the number of variables appearing in d theta will decrease by, one by one. So because there are only finitely many, the variable appearing in d theta, it will eventually becomes 0. So it will all disappear. So that's why it terminates. The number of variables is decreasing. So this is a typical argument. Some measure which is bounded below is keep decreasing in each iteration of the loop. So that's a typical way of showing termination of the algorithm. And then second, why this algorithm does the right thing? Because of the loop invariance. And the loop invariant we're gonna talk about is the following. It say that so these are given set of literals. So it says for any unifier, theta prime of D, the following is true. Okay, this theta is something which is updated by this algorithm. See, okay, right. So and then the condition sets, if we compose theta together with theta prime, okay. So first run substitution theta and then theta. So we compose these two substitution diagrammatically. That's exactly the same as theta prime. It's a bit weird condition because it looks like how come this happens, but it happens. So if you compose the current theta with theta prime, that becomes exactly the same as at unifier theta prime. So that's going to be the loop invariant. Now note that this loop invariant doesn't say D is unifiable. It just said if D is unifiable by theta prime, then this unifier have this form. If D is not unifiable, this kind of claim is not going to be, it will never be true because there is no unifier. So this is a conditional statement about if unifier exists, that unifier should satisfy some specific property. So that it turns out this is a loop invariant, and then this loop invariant is strong enough to show the correctness of the algorithm. So that's why we're going to look at more detail in the next slide. So the proof, for termination, as I mentioned, if you do not hard, the number of variable gets replaced by, so the number of variable replaced by a term that doesn't contain x, so the number of variables is decreasing. And then now for the loop invariant, this is a loop invariant that I just told you. So maybe an algorithm here. Okay, so the loop invariant is this one. For any unifier, if it exists, so then, if theta prime is a unifier, so then you should have satisfied the following property. Theta prime, same as theta, which is currently being updated by the algorithm. And then this theta prime is, so compose theta and theta prime diagrammatically, that gives the same thing as the theta prime. Okay. So loop invariant means that it's true when we hit the loop for the first time, and then also the body of the loop preserve this property. So that's what the loop invariant, the word loop invariant or phrase loop invariant means. So we have to show that it's the case. And then when you hit the loop for the first time, this property is always true. So this property will be true. That's because when you hit the loop for the first time, theta is an identity substitution. In other words, it's an identity map from sigma terms two sigma terms. So if you compose, first run the identity function, and then run some other substitution theta prime, that of course it should be the same as theta prime. So when you hit the loop for the first time, then this relationship will be true because theta is an identity substitution. Okay. Now, when the difficult part is to show this is a loop invariant, it's preserved by the loop, which means that when we enter the loop, so when you enter the loop, if this relationship is true, so for any unifier theta prime for D, we have this relationship. Unifier for D. So this is a relationship which we can assume to be true. And then now if you, to talk about it's maintained by the loop, which means that when you go back to the loop, this will continue to be true. We have to show if the execution somehow goes through, and then you go to the, because you go to the else branch, you will get out of. So if you just go to the true branch, so then we're gonna update theta to, of this form. So for this updated form, the same statement should be true. Okay, what does that mean? That means for every theta prime, T of X, that has to be true for any unifier for D. So here I use a theta and theta to mean the same thing. So this is the theta will be updated to this guy. So this is the new theta. This is the old theta when that we use it when you enter the loop. So for the old theta, because the loop invariant argument say we can assume, well, this loop invariant is true. So this is what we are assuming. What we have to prove is that when we get to the end of the loop and come back, this property continue to be true. So when we come back, our new theta is of this form. When we use the old theta, so it is always this form. And then we have to show that this relationship is true. And now here's an argument why that is the case. So now, so to show this guy, let's pick unifier theta prime. So I think let's pick any unifier theta prime for D. So that's what we did. We pick any unifier theta prime for D. So then by induction hypothesis, which is some fact that we can assume to be true when you enter the loop, we know that this relationship is true. Okay, by the assumption that we can make. So because this assumption is true, and then we know that theta prime is a unifier for everything in D, this relationship has to be true. And why this is the case? This, if you remember where X and T comes from, this X and T comes from what we get from d theta, where we have some term X. We have, in one case, we have variable X, and the predicate symbol P, another corresponding position, we have a T. That's what we have for d theta. Okay. But because of this relationship between theta and theta prime, so if you apply theta prime here, so then that's going to be the same as d theta prime. So as I said before, for literals, the applying substitutions one after the other is the same as first composing two substitutions and applying it in one go. So these two things are the same, but this is a unifier. This theta prime is a unifier, so it should be a singleton set, which means that this guy and this guy should become the same. So what does this mean? This means that if we apply theta prime on this, okay, so if you apply theta prime here, theta prime here, I mean, these two things should have the same thing. For this to happen, theta prime applied to x and theta prime applied to t should have the same value. So just to say it again, our theta prime is a unifier for d, and then theta prime and theta will satisfy this relationship. So unifier and satisfy this relationship. If we combine these two factors together, that means t of this one term and variable selected by the algorithm should map to the same thing by theta prime. Okay, now for the next step is, I think I have to erase all the things. So next step is, because these two things are the same, then the relationships, this relationship is true for theta prime. Why this is the case? So we this one say, if we apply theta prime on x, theta prime on t, that's the same. Now, if you compare these two terms, the term on the left-hand side of the equality, term on the right-hand side of the equality, maybe erase. Okay, this guy and this guy, and the difference between them only happens on variable x. For all the other variables, they behave exactly the same. Okay, for variable, because the first replacing x by t, it won't change any other variable at all. So the only thing we have to make sure is that this, the guy on this left-hand side, the guy on the right-hand side map variable x to the same thing. And that is actually the case if you apply substitution theta prime on x. So actually this is better. For x, if you apply this substitution, dx given theta prime, that's the same as applying substitution first and then theta prime next. Now, if I apply this first substitution, that's going to be same as a t. Now we get theta prime. But because of this equality, this t, applying theta prime on t gives the same thing as applying theta prime on x. So that's why this equality is true. Okay. Let me erase this much. Okay, so from there we can deduce the new loop invariant is gonna be reestablished at the end of the loop because of the reasoning that you see on the screen. Now with theta prime is, we have theta prime same as theta dot theta prime. And this is coming from our hypothesis, which we can assume when we do the inductive proof. And then for this fact tells us we can replace theta prime by substitution to get followed by theta prime. So that's what we begin in the next term. Now, if this dot is a function composition, so we satisfy associativity. So if you rearrange this parenthesis, this is what we get. Let's erase this. So this is what we get. But now what we have now is that for every theta prime, which is a unifier for D, we have this relationship. Theta prime is the same as, this updated theta followed by theta prime. That's exactly the condition that we want to establish because, this term, updated theta is exactly a new theta to be computed by the algorithm. Okay, so we have just shown that this theta prime is equal to theta composed with, followed by theta prime is going to be maintained by the body of this loop. Okay, so that's the proof of the loop invariance. Now I want you to think a little bit about the next step. You can use this loop invariant to prove the theorem. So the theorem say, which is the correctness of the algorithm. So what we have to prove is that if the algorithm returned fail, then actually this D is not unifiable. And if algorithm just output theta, that's the most general unifier. So I'll give you 2 minutes to think about this. So this is what I want you to think about. Okay, so we can show the second one first. So it said if the algorithm terminates, okay, so that when it terminates, we know theta, so this show the second. If the algorithm just terminate and return theta, we know theta is a unifier because of the loop condition. When we get out of the loop, only when theta is a unifier. So we know that theta is a unifier, and then loop invariant to say for any other unifier, we satisfy this relationship, which means that theta is the most general unifier. Okay, so this implies the most general unifier, so that's okay. For the other case, if the abnormal termination, which means the algorithm just returned a fail, so then we say we want to conclude that D is not unifiable. Okay, how do we do it? We can do it by contradictions. So we said, suppose D is unifiable. So then we want to say there is some contradiction, so D can't be unifiable. So that's what we want to prove. Suppose D is unifiable, then there is a unifier theta prime. So then by the loop invariant, okay, which applies to any unifier, we set the following relationship is true. Theta prime is equal to theta dot theta prime. What does this mean? This means that when for d theta, if you apply substitution theta prime, that's going to be the same as d theta prime because this composition is same as theta prime. So this will be a singleton set. In other words, well, sorry, I just stopped the screen share. It all disappeared. Okay, so the proof step we said theta dot theta prime same as theta prime, which is a singleton set. Say suppose it's unifiable by theta prime. So And then this is the case. That means d theta is also unifiable, because by applying theta prime, we can make them into a single literal. Okay. So, but that cannot happen, because after applying d theta, we have two terms which will never be unifiable, because in one terms, I mean, both of them maybe have you start with the two different function symbols, or maybe variable x, one is variable x, the other is a term t which contains variable x. So the violation of this condition means that the theta is not unifiable. So these two contradict with each other. So say, assuming d is unifiable and loop invariant implies that d theta is unifiable. On the other hand, the conditions of the algorithm say d theta is not unifiable. So they contradict with each other. So that shows the desired contradiction. Okay. So that implies if we return the failure, this d is not unifiable. Okay, so now what we're gonna do is we will use this unit. So we have a theorem, but really the theorem is about the unification algorithm. Then we're gonna use this to design a first order logic resolution. Okay. So in the first order logic resolution, we are given so the key concept, just like a usual resolution proof system. The key concept here is resolution proof step, but this proof step involves two things. One is trying to figure out appropriate substitution. In particular, we are looking for most general unifier. And then we will also do the cancellation. So, this proof step in the first order logic resolution is captured by the concept of reservant. So reservant is defined this way. So if we have a C1 and C2, they are clauses, first order logic clauses with no shared variable at all. Okay. And then we say R is a reservant of C1 and C2 if we can find a subset of literals of D1, subset of literals in D2, such that essentially we can compute most general unifier and we can do cancellation. So that's what these two conditions are telling us. So we said D1, these are the set of literals, and then if you take a union of D2 where everything is negated in D2, okay, and then they have a most general unifier. So this is involving this substitution or instantiation that I talked about. And then second, if this R is obtained by applying this most general unifier theta on C1 and C2, and then doing cancellation, canceling the corresponding literals or complementary literals. We apply substitution on C1, so which means that everything in D1 will become the same thing, the same literal L, because theta is a unifier for D1. And we apply theta on so apply theta on C2. That also means that everything in D2 will become the same thing. There will be a complementary literals of L, so that's why we can put L bar here. So we get rid of, after we first apply substitution that we computed in the first step, and then we get rid of the corresponding canceling literals, then take the union. So that's what's gonna give us a new reservant in the first order logic resolution. The second condition said, in case that if C1 and C2 have some variables in common, then we can do pre-processing, which is renaming those variables by something fresh, so that these two clauses C1 and C2 do not have any shared variable, and then we can apply the resolutions. This is this proof step in the first order resolution, compute the reservant, and we still call it reservant in this more general case. Okay. So the key things happening is the old propositional resolution proof step, we only do the cancellation. Here, we compute most general unifier, apply this most general unifier to the given two clauses, and then do cancellation. So these identifying most general unifier, applying it happens in the additionally in this first order logic resolution proof step. Okay, I think the best way to see how it works is to see some examples. So here are some examples. So we have about 7 minutes. So I mean, so solve this example. I will show you the idea of resolution here. Okay, so compute a resolvent in this case. So I will give you 2 minutes to do so. Okay, so how to solve this? So, I mean, here's the plan of doing resolution. I mean, at the end of the day, we have to do cancellation. So we were gonna try to cancel this guy with this guy. But we said in order to apply first order resolution proof step, these two clauses shouldn't have any shared variable. So we're gonna rename variable x. So I mean, we're gonna rename x to u. So after the renaming, we'll have not of p set f of e u f g of e. So variable x here is renamed to variable u. And then we're gonna try to find so we will try to cancel this term with the corresponding term in C2. And then to do so, we have to call most general unifier. So next step is we call most general unifier on set, which is a negation of P f of E U f of G of E. And then we put the negations on the formula, on the literal that's coming from C2. And then write it f of x, y, f of z. So we call this algorithm the most general unifier algorithm in the proof of this theorem that we see. And then, I mean, I'm not going to go through all the details of the algorithm, but essentially the algorithm computes by saying we have to replace x to e, y to u, and then z to g of e. So the MGU returns a substitution which say x should be replaced by e, sure. So, and then, okay, y should be replaced by u, and then Z will have to be replaced by G of E. Okay. And then the next step is we apply this substitution to C1 and C2, cancel the corresponding literal. So cancel in this guy and this guy. And then the only thing remains is this one in from C2. So then the outcome, the reservant R that we can compute in this case is going to be negation of P, where X is, we after substitution, X becomes E. After substitution, Y becomes U. After substitution, Z becomes G of E. Okay, so that's what the reservant that we can compute from C1 and C2. Okay, so I think I will stop here, and then we will finish off this first order logic resolution on next Monday. Okay, I will stay here for about 5 more minutes, and if you have any question, you can ask me.